This VSEPR table highlights the standard H₂E2 geometry used in almost every introductory chemistry classroom. To predict the shape of water, students learn a specific mental model: two identical rabbit ear lone pairs pushing the hydrogen atoms downward. This model assumes oxygen undergoes sp3 hybridization, resulting in 4 equivalent orbitals. 2 form bonds with hydrogen, while the other 2 house the non-bonding lone pairs. The core premise is steric repulsion, the idea that lone pairs are larger and more repulsive. To minimize clashing, they expand, squeezing the OH bonds and closing the angle. This visual mnemonic is a staple of chemical education, appearing in nearly every high school and freshman level textbook. While VSEPR reliably predicts the geometric shapes of simple molecules, the physical assumptions it makes about how electrons actually behave are false. But when we rigorously test these classical assumptions against modern high-level quantum mechanical calculations, the entire VSEPR model completely collapses. This source image shows the actual electron density of a water molecule, calculated through density functional theory. Notice the distinct shapes of the HOMO and HOMO-1 orbitals. Across every valid computational model, the 2 lone pairs are completely inequivalent in shape, orientation, and energy. The actual orientation is specific. One lone pair exists purely within the molecular plane, while the other sits perfectly perpendicular to it. To understand real molecular mechanics, we have to move past VSEPR's steric assumptions and apply rigorous quantum symmetry rules. Mastering chemistry requires graduating from qualitative textbook heuristics to actual physical realities. The foundation of this model lies in atomic orbital symmetry. Atomic s and p symmetries can only be broken by chemical bonding interactions. Because no bonding interactions occur outside the molecular plane in water, the out-of-plane pz orbital is mathematically excluded from hybridization. This symmetry rule dictates the result. The orbitals resolve into one unhybridized pure p lone pair and one s-rich lone pair locked in the molecular plane. We can visualize these localized structures using natural bond orbital, or NBO, analysis, the tool used to extract Lewis-like structures from complex wave functions. These NBO plots confirm the physical separation. The right contours show a spherical s-rich orbital on top and a dumbbell-shaped pure p orbital below. No mathematical transformation can force these into equivalent rabbit ears. VSEPR's sp3 assumption contradicts the system's required group theoretic symmetry. This isn't just a theoretical discrepancy, it shows up in observable physical properties. Take the classic case of hydroxylamine's dipole moment and rotational barriers. Using VSEPR, you would assume large, equivalent lone pairs on oxygen. This leads to the prediction that the lowest energy state is the staggered conformation to avoid steric clashing. However, experimental dipole data shows that the staggered conformation is not even an energy minimum. It sits on the side of a hill on the rotational energy surface. NBO analysis resolves the error. The actual s-rich lone pairs are compact and low energy. They don't cause the steric clash that VSEPR assumes. We see the same failure when we look at the aromaticity of furan. If furan's oxygen possessed sp3 rabbit ears, neither lone pair could align with the ring's pi system, which would violate Huckel's 4n+2 rule. This bottom panel for furan shows how NBO analysis clarifies the geometry. The pure p lone pair sits perfectly perpendicular to the ring, allowing the molecule to maintain its aromatic character. From dipole moments to aromaticity, VSEPR consistently leads chemists to incorrect physical conclusions. This raises a question. If lone pairs don't physically repel and squash bonds, why is water's bond angle 104.5 degrees instead of the tetrahedral 109.5? The actual driver is Bent's rule, which states that central atoms direct higher p character toward more electronegative ligands. The Coulson equation defines the exact relationship between orbital hybridization and bond angle. Shifting p character narrows or widens the angle. In water, the lone pair acts as a ligand with 0 electronegativity. Demanding no p character, its excess p character reallocates into the OH bonds. Higher p character in a bonding orbital naturally narrows the angle between those bonds. The angle tightens because of orbital rehybridization, not because a fat electron cloud is pushing the bonds down. Molecular geometry is driven by the reallocation of p character based on electronegativity. The VSEPR concept of steric squashing is obsolete. chemistry is moving beyond qualitative shortcuts to embrace the mathematical reality of electron distribution. VSEPR remains a popular introductory mnemonic because it often generates the correct gross shapes for simple molecules by accident, but it fails at the quantum level by inventing repulsive forces and physically impossible hybridizations. The truth, proven by NBOs, is that lone pairs are strictly inequivalent. One is a compact, unreactive S-rich orbital, and the other is a reactive, out-of-plane pure p orbital. Chemical reactivity and resonance depend entirely on understanding this true quantum geometry. To practice chemistry at a professional level, we must unlearn the anachronism of rabbit ears and analyze structures through natural bond orbitals and Bentz roll.